I'm William Quinn with Global PAM. I'm the Director of Engineering. And we have a quick presentation here on some of the fixed plant items, and really, to be very specific, actually on mill gearing. And the same can actually be applied for kiln gearing as well. Get into some of the iron ore sites, and then also within the cement and pulp and paper industries as well. So what we want to go through here is kind of a basic high level asset management structure, and I'm sure this is potentially very basic for a lot of you, but you know, the more we standardize on how we look at assets and how we approach managing those, the better off we'll be you know, down the road, and especially as a service provider that we are, where we go to a lot of different sites, it starts to help us interact with the teams as well in a much more uniform manner. And then we'll go through a kind of an RCM approach, which is integrated into that asset management structure, as well as kind of a case study of how these methods can be kind of applied, where you go from the actual asset management structure down to kind of the maintenance reliability stage, you know, all the way through actually, you know, basically replacing that in some questions. So a little bit of background on Global PAM, if you're not familiar. We provide basically comprehensive support for critical assets operating in mining and heavy industry. As I mentioned, cement and pulp and paper are some of the other industries we work in. We provide specialized support for mill and kiln gear systems, and our engineers and technicians are really experts in their specific subject fields, basically ensuring that we're providing customized solutions to our customers' assets. So we're generalists, we try to be specialists. And support basically encompasses the entire asset lifecycle for those assets under our portfolios. So as we get into girth gearing, if some of you come from the mobile side, basically what we're discussing here are the gearing that drives the mills. And so if you're not familiar with a mill, basically, you know, we have ball mills and SAG mills, and basically large, basically taking material from a crusher and then grinding it down to specific sizes, typically in a wet process to get a slurry so that we can actually send it out to flotation. And we're just, again, specifically looking at the drivetrains. So if we're looking at the drivetrain for this this large rotating drum, we have AGMA ratings and design verifications that are available that basically set the standard for the acquisition of this equipment. So there's standards for manufacturing that can be specified and should be specified at the procurement stage. This is important because a lot of times a site will have an issue with gearing and end up just saying, I want another one of those. I want a replacement of that, and then shop around for price. And where you can fall into traps is this scenario where we have, you know, no specifications have been set during that procurement stage, and then it comes time to ship something and there's quality issues. And basically the manufacturer is going to get uptight about not actually, you know, saying, well, that there was no procurement specifications that were included in that. And that's one of the issues that we see somewhat often, where there's just no specifications being sent to that procurement stage. So we also then look at, you know, actually doing audits during that manufacturing process and during those critical witness points, and then basically signing things off prior to the shipment. Now, if things go through a typical OEM, they'll take care of a lot of that process. But it's just important considerations to make when you're purchasing, you know, a very expensive piece of equipment. I mean, mill pinions such as this range from anywhere from $90 to well over $150,000. And then when we get into the mill gearing itself, it ranges anywhere from, you know, $250,000 upwards to $1.4 million, depending on the size of the gearing. So it's also then important to move on to the commissioning phase and ensure that the proper installation procedures are followed. Again, a lot of this can come from the manufacturer or the OEM, but it's just sometimes important to have third parties involved to make sure that those processes are followed and the correct industry standards are followed across the board. and that you have all the critical steps are documented and available for future reference. And really, the documentation side of this is very, very important. And it's very difficult when we come into plants where something was installed maybe without the proper documentation to do maintenance work, because you're always looking for maintenance records. And okay, if I need to know what the runouts were on a particular gear to set a pinion properly, and we can't get that data, we then have to spend a lot more time retaking data, which ends up causing more downtime for the plant. So it's really important, if you put new equipment on, to record that information and keep it readily available as well. Then as we get into the kind of logistics support stage, it's really important to kind of look at things from a decision analysis standpoint, where you're trying to do a lot of optimization of basically, now you have maintenance costs that you're starting to incur on the asset. Sparing costs become another phase as you get further into the asset life, where the risk of failure may be increasing based on the condition of the asset. And we start to look at what are those costs, when is it timely, and when does it pay to have that spare, and that really depends on the layout and of each individual plant. A plant with 2 small ball mills is going to have a very different sparing need than one with 15. And included in that is the insurance costs as well. I mean, downtime risk insurance is a big driver at a lot of plants of some of the maintenance practices that they're actually implementing. Once we get into the operation and maintenance phase, we recommend an RCM-based approach, which is reliability-centered maintenance, and basically audits of those existing maintenance plans, and basically ensuring that you're following somewhat of a standardized approach to maintenance, so that we don't have plants that are missing particular PMs and things that really should be done. So then we move on to the end of life. So now you've gone through that maintenance phase, and we have a breakout section on the RCM that I'll go into here shortly. But during the end of life, you have the RCM basically should be the guide to when your expected cost value of operation basically exceeds the replacement cost. So if you're using cost justifications, you can get to the point where it's more costly to do repair or remediation versus replacement. And some of the other things that we've started to look at, we don't have a super strong data set yet, but once you start to get gearing that's worn and that's damaged, you start to lose efficiency of the gearing as well, and power generation, power consumption really in a mill is really highly concentrated around the mills. And so there can be a point where if the equipment is damaged sufficiently, that you start to look at actual power loss conditions that may be driving your cost function as well. So again, we look at this in terms of the conditional probabilities of failures, which should be updated based on basically predictive maintenance tasks and inspections. Within that, the real options for mill gearing is you have the option for flipping, replacement, or refurbishment. And refurbishment is quite rare in that usually it's very costly, and you're left with something that may not have the full capabilities as the original equipment or something that's brand new. And pinions are also suitable for flipping and or replacement. So we'll dive into the RCM approach, which I think a lot of you are probably maintenance personnel, but basically there's 7 basic questions that get asked for that. So each girth gear system or asset needs its functions and desired standard of performance clearly identified in its present operating context, which really means, how do you plan to run this? Are you going to run it is it a a piece of equipment that's rated for 3,000 horsepower and you're going to run it at 4,000 horsepower. Something like that would be very critical to determine if it's going to be overloaded, and really how it can run based on those loading conditions. And then go through how it can fail to fulfill its functions. And those are things where, we have a pretty good database of gearing that we've seen at a variety of different sites that have enabled us to basically look at these specific types of gears and how they tend to fail. Then you determine the cause of each functional failure. So now you have your failure modes, and determine what happens when each failure occurs. So now you have your failure effects. Then classify those consequences of failure, or essentially consequences, and determine what should be performed to predict or prevent each failure. So that now you get to the tasks and task intervals. So, a lot of the items that have been talked about today are, basically predictive maintenance or predictive sensors, where we're looking at, different sensors and different items that can be done or implemented into various assets to basically look for those failure modes early on in their life. And so, the world is really moving in that direction of trying to gather as much data as we can off of these assets. And it's really to help fulfill this framework. And then, at the end, if basically one-time changes can't be, or if these failure management strategies are not effective enough, one-time changes are needed, which would be engineering or design changes. So going to complex asset failure patterns. So this is basically an excerpt from an RCM handbook from the United States Navy. And when we look at the population of girth gears as a whole, we tend to find that there's a pretty flat conditional probability curve for them. You could argue that there's maybe a little bit of a early mortality type, but really when we start to look at them, it's pretty random. We have gears that are 3 years old that have had a lot of issues, and gears that are 30 years old that are also having significant issues. And so, you start to look at the population, and this really is what should be driving how you're putting your maintenance plan together for that particular asset. If you're looking at it on a flat conditional probability curve, it basically will start to drive your predictive maintenance tasks and also the other maintenance procedures that you're going to be attempting to do. So at a high level, we'll go through this specifically for girth gearing. So now we have the girth gear system function is basically to rotate a cylindrical drum, transferring and increasing torque from a high-speed shaft, a pinion shaft, to a girth gear. You're looking at 95% uptime, around 8,300 hours per year is usually an aspirational goal for a mill. Girth gear functional failures, basically pretty simple. Girth gear can't transfer the torque. The pinion can't transfer the torque. The failure modes, the big three categories that we can break the girth gear down into is a structural failure, a joint failure, or really a tooth fracture, which is the predominant mode since that's really what's being acted upon as the gear is driving. And if we start to look at the tooth fracture as a specific mode, then we get into the failure effects from that tooth fracture. So a fracture can include high vibrations, loud noises as the broken section comes through mesh. You have additional teeth that also can break from impact to the broken section. The gear and pinion at that point really need to be replaced. Right now, we got a couple guys actually looking at a mill in California that has 29 cracked teeth and fractured teeth. So it does happen, and it's one of these things where we really want to get to the point where we can start to more accurately predict and prevent those fractures from occurring. So what we have presented here is essentially a potential failures and the failure mode relationships. And so we have kind of closer to the left-hand side of the screen, the specific failure modes and how those degrade basically and can lead to that ultimate failure of a tooth fracture. severe abrasion, adhesion, scuffing, indentation, cold flow, tip to root interference, tight mesh, macropittic spalling. So some have wear-related phenomenon where we have contamination, or you have loss of lubricant type of functions where we're getting scuffing and or adhesive wear. And that's something that will then degrade over time continuously if we don't have, if there isn't a mitigation process put into play. We also have macro pitting and some of the other overloading type of failure modes, but also they can also be related to purely fatigue related phenomena where the gear has just reached its contact fatigue limit. And on the left, we also have some of the tools that are available for predicting and detecting those failure modes. One is the ASTM E2905 method, which utilizes eddy current array for inspecting the girth gear teeth. They also have visual inspection, which can usually combined with the E2905 method to look for different failure modes that you may need to be just identified visually versus something that's being done with purely an electromagnetic method. And then other methods really should be controlled within the design and manufacturing step, where we look at hardening cracks, grinding damage. I mean, carburized pinions in particular are prone to grinder burn and other types of manufacturing damage. But those are also generally detectable with the other methods if they do make it past the manufacturing step and into operation. And the whole objective is to catch these failure modes early, monitor them, and then get them addressed before they lead to that tooth fracture. So an important item to address within looking at any asset is really determining how often you need to do a failure finding type inspection. So now we're looking at predictive maintenance tasks, such as the ones mentioned in the previous slide, where we want to make sure that we're doing those at an often enough occurrence so that we have a good probability of detecting the actual failure at an early stage in order to do something. So these are just two graphs that kind of show what those inspection intervals can look like. And as we move into more autonomous type inspections, that those intervals start to become milliseconds. And so we really start to gain a huge advantage on this type of PDAF curve. But for the more manual inspections, such as the ones that we're doing on the girth gears, we tend to look at 1 year inspection intervals as sufficient to catch early stage cracking before it turns into full tooth fracture. Now that rule applies the vast majority of the time, but if multiple failures start to occur, such as significant misalignment occurs and no other maintenance tests are being done, such as stroboscopic or temperature monitoring by the site or by autonomous systems, failures can develop in shorter time periods than that. So as we move through that RCM process as well, we get into the failure effect consequences. So now we're looking at how this actually affects the operation. And basically this failure mode can result in extended downtime when the gear and pinion are replaced. If a spare is not available, the downtime can be catastrophic. So, most of the plant, the mills that we're working with, depending on the material being processed, but you're looking at anywhere from $30,000 on the low end per hour up well over $100,000 an hour for mill downtime. So it's really critical to find these failures early and get them addressed before they cause a significant amount of downtime. And the secondary, piece of that makes it even more important is the lead times of gearing. I mean, typical lead times right now for girth gears are hovering around 40 weeks. I've seen some around 30 weeks in the past couple of months, but there's a significant amount of time to get a replacement if there is not a spare on site. So When we get to what needs to be done to predict or prevent those failure modes from tooth fracture, on-condition tasks need to be implemented to check for potential failures, as mentioned before. And the big ones that we're looking at is crack formation, severe wear, and spalling. And in order to avoid basically that developing into a cracked or fractured tooth. So these inspections need to be done, as I mentioned, much more often than that PDAP curve. And what we've seen for a couple failure modes, and I'll get into an example shortly, is that the crack formation and propagation tends to happen at intervals of much longer than a year. But it does not rule out the fact that we need to do regular visual, stroboscopic, thermal imaging, and vibration analysis, and as well as lubrication analysis to keep on top of things that can start to cause failures much more rapidly. For instance, if you lose lube on a gearing system, you can cause a failure very, very quickly within hours or a day or two. So here's a quick example of SAG Mill gear. The nameplate power on this gear is about 17,000 horsepower, so it's not a small piece of equipment. And up until the failure, really, there was about 43 million load cycles. There's about 35,000 hours of life on this gear. So most of the gears are designed for 219,000 hours of life. So this was quite early on in this gear's life where it started to develop failures. So here's a quick overview of a SAG mill. As you can see, it's a fairly large piece of equipment. So right off the bat, the site was doing annual inspections, which was a good task. So they were really following the recommended maintenance procedures for this asset. A complete basic cleaning and girth gear inspection was done on March 15, 2016 per ASTM E 2905. So we're using eddy current array, and they detected 4 cracks. Those then were relieved, and the prior inspection a year earlier did not detect any cracking. And the nice thing about the data that we have with the eddy current array method is we can go back and actually look at the previous inspections and look and say, okay, yes, there was no crack on to 189 in 2014. And within that 2-year time period, cracks had developed. So this is, again, some of that additional support for doing those inspections annually, where if we'd done inspections in 2015, we may have been able to find some of these cracks earlier on in their life. So the initial crack detection kind of shows it with this magnetic particle inspection. You can see on the image, mainly on the right, some of the yellow, where the magnetic particle is sticking to the crack on the tooth. So we have a mitigation technique where we do some relieving of the crack itself, and then some area right adjacent to the tooth. And with that technique, and then monitoring every month, we basically were able to prove out the technique as being quite effective at slowing the propagation of those cracks. Dicom blue is then used to monitor the contact vicinity of the. So with follow-up inspections, we were doing monthly MPI and also ultrasonic inspections to look at the depth of the crack and look for large deviations in depth as well. There's a strong correlation between surface propagation and depth propagation of cracks, but having both those methods employed just ensures that we're catching any kind of propagation that might be significant where additional action might need to be taken. A secondary inspection was conducted at 11 months. We recommended doing this every 4 months, but due to downtime constraints, we weren't able to conduct that. And I'll show you shortly the additional cracks that are found within that. But here's just some of the ultrasonic mapping of a crack, and then here's it monitoring it over time, showing fairly indications at depth. And then towards the right hand of the screen, some additional propagation was found at the surface, and you can see it started to propagate at depth as well. So additional cracking was found about 11 months later. And we went from, at that point, we went from 4 cracks up to about 10 cracks, and found additional cracking on teeth. So the initial failure mode that was causing this was primarily indentation. And once those indents had formed, the cracks started, and those cracks continued to propagate. during that time period. And so we had cracks that were not there previously that started to form and grow even during the time that we were doing inspections and monitoring. So here's a quick graph of the cracks and shows some of the propagation. And most of the propagation was concentrated around incidences where the crusher had gone down and they started pushing more load through the SAG mill itself. So, highly correlated to how much loading was being applied to the gearing. And in addition to that, there was additional liner bolts that failed, inducing more contamination into the mesh as well. And so, in accordance with kind of our asset management structure here, once this cracking was found, the site started looking at the replacement gearing. They did not have a spare, and so on the back end, the process was started to procure that new gear and work with the manufacturer on ensuring that all the quality assurance documentation was done properly, and that it was manufactured to the highest standards, the highest industry standards. That's typically AGMA 6014, and B15 is the most recent revision for that. And then, all the way through ensuring that the installation was done properly, and that the gear operates as best as it can in its current operating context. So, does anyone have any questions?
Do we have any questions from the audience? You can also go ahead and ask. Okay, here we have one. At what point do you recommend flipping the gear to minimize further cracking to maximize the useful life of the gear?
So I used to work for Falk, which was a manufacturer in Milwaukee that made large mill gearing, and we did one instance where we took the gear out and we flipped it into we flipped the gear over to put those cracks now in compression. Now, the unfortunate reality is they spring back essentially after every cycle. And so with continued monitoring with that gear, we found the cracks continued to propagate. So at this point, we don't recommend flipping a gear that's cracked, mainly because you go through you have to go through the full installation phase. And so there's a lot of cost that's tied up in that. And then you still end up with those cracks likely continuing to propagate. And so the best course of action is really just remediate it and operate the gear with the cracked teeth as they are. If you can, if there's not multiple fractured teeth in a row, I mean, that's a slightly different scenario that's got to be addressed differently. And then to replace the gear once that replacement is available. So yeah, typically if you get to the phase where you're cracked, the gear really just needs to be replaced. Flipping that gear is not a great option. It's much better to flip the gear when you have some macro pitting or some abrasive wear on the teeth, and it's at a point where you're starting to see significant vibration impacts from the operation of it.
Perfect. There's another question from Jeremy. Can you speak a little bit more about what you consider best practices maintenance, particularly intervals for visual inspection and ASTM analysis? Yeah.
So when we're looking at visual and you're looking at basically complete NDT inspections of the girth gear teeth, we currently look at 1-year intervals as sufficient for most gearing based on its condition. If we come into a site and they're already starting to experience severe macro pitting and there's been a quick degradation in that macro pitting, so it wasn't there, now it's started to progress, we'll recommend intervals shorter than that. But for a general, intervals are sufficient for that kind of intrusive, removed guarding type of inspection. But we highly recommend that people look at their mill gears at least once. I like to see it once a day if they can open up the inspection ports and do stroboscopic inspection, look at temperatures of the mesh. And you'll catch a lot of potential failures on the pinion, which will kind of act as a canary for the gear. If things start to go wrong with the pinion, it can indicate alignment issues with the gears.
Perfect. A question from Tom. How long does it take to clean and inspect a mill gear?
So it typically, if we look at it from a cleaning and inspection perspective, we can do most of that work within. So then move into the inspection phase once we have access to the gearing.
Perfect. And I see one last question from Simon. Have gear specifics evolved in the step with global manufacturing capabilities? Example here.
The herringbone gears.
Yeah, we're too technical. We're popular in the past, but very few places can manufacture them today.
So the global, I can really speak to the 6014 specification, and that's a specification that has evolved over time. Herringbone gears are very, they're nice in one way in that they don't have any thrust forces acting on them, but they also seem to present a lot of maintenance challenges where we run into sites where they were originally designed to run on Babbitt or sleeve type bearings, and now they've been switched over to spherical roller bearings. And then, within that, spherical roller bearings can handle thrust. And so what we've seen is people locking up certain helices on these herringbone or double helical gears and overloading one side of them when they've been either moved to a different site or even at a site where they've just done some overhaul of the drivetrain. Now, I agree. The manufacturing capabilities have changed. We're looking at most manufacturers using form type grinders or large hobbing type cutters, including some that are single indexing gashing type cutters as well. And with those, you can't cut through the helix because you'll cut into the other side. So we have to have a gap in there. So the reality has been is they went from herringbone to helical gears because the bearings technology improved with the real strong advance in spherical roller bearings, especially on the pinion pillow box. You can handle the thrust loading that's present on helical gearing, and so we get all the advantages of having a good axial overlap between the teeth, and we can handle the thrust that's generated from it. Where in the past, most of the mills and the gearings were more constrained and concerned about the bearings, and so it was cheaper and more effective to make a double helical type gearing to neutralize the thrust. I don't know if that totally answers the question, but they're hard to get manufactured without increasing the gap width. Is what it comes down to.
Okay. Looks like Jeremy asks another question. Are you seeing sites implementing real-time monitoring for temperature or maintenance metrics?
Yeah, that's becoming more popular, and it's something that we're fairly adamant about as well. Is implementing continuous online temperature monitoring is very important. Help catch two very quickly. One is if you have a lube type failure, you can have if you have a lube type failure, it'll catch that spike that may be generated from the temperature from a temperature there. And it also looks at alignment type issues where if the pinion and the mill become misaligned, either due to some damage to the trunnion, we see sites where we've had wear within the bearings that support the mill itself, and then you also can have wear and issues within the pinion pillow box as well that'll start to cause misalignment. Another source of misalignment is becoming more prominent as we've gone to much larger diameter mills, some SAG mills that are they're pushing the design limits of all the materials, and everything is getting designed now with an FEA type model. And in doing so, the safety factors and some of the service factors have been reduced, and so there seems to be more distortion and more distortion in the actual shells than in some of the older models. And what we'll see is when liner changes are occurring, that will actually get some distortion of the shell, and it'll cause misalignment within the pinion and the gear on some of the larger. These are mostly newer SAG ball mills that have been manufactured in the last 10 years or so. So it's the online temperature monitoring is really important to catch that. And then we're getting to the point now with some sites where we want to be able to take, as if liner changes are being done, basically based on history, trying to determine how far that pinion needs to be adjusted to do all the maintenance during one shot.
Perfect. And one last question before we move into the wrap-up. A question from Graham. Has there been much effort in making the actual change out of pinions and gearing more time efficient?
There's been some, I would say, movement. I think because it's such a rare event, I don't think there's been a lot of research and development into making that actual change out much more time efficient. If a gear is maintained properly, it'll run for around 25 years. But having said that, I mean, proper project planning going into the process and having really taking runouts and doing all of it, it's all anchored in math, in fundamental mathematics. And so if you have the right processes in place, the process can be done in 6, 7 to 10 days, depending on how the project plans, the size of the gear, and really availability of cranes and other items. I mean, there's a lot of variables that go into it. So